So previously we've talked a lot about different coordinates. We've talked about spherical coordinates, we've talked about cylindrical, we've talked about polar coordinates and rectangular coordinates. Well, what if you want to invent your own coordinate system that's useful for a particular problem that you're solving? How would you go about doing so and then converting, say, a double integral into these new coordinates? Okay, this is the topic of changing variables, and here we're dealing with now general coordinates, which we're just going to call u and v, and they have different expressions depending on the application you're looking at. Although you may not be convinced that you've done something similar before, you actually have. If you've ever used u substitution to compute an integral, then you've actually dealt with a change of variable problem where you decided to use the new coordinate u instead of the old coordinate x. And we'll go through the steps in light of this new way of seeing u substitution, and that will give us a foundation for then discussing double integrals using general coordinates, and we'll learn how to then change variables for our double integrals. And what we mean here by general coordinates is that, they will be different depending on the application. So we're discussing coordinates generally. I don't mean general coordinates in that there is a coordinate system called the general coordinate system. Just a minor note there. So we have this coordinate system, we have this integral in the coordinate x, and what do we do for u substitution? Generally, you'll look under the square root and you'll set u equal to that, okay? We're going to let that be the inverse transformation, okay? This is going to be the inverse transformation, so that when we invert this function to get x in terms of u, we have this expression here. We're going to let that be the transformation, okay? We're going to call that the transformation. So it's x in terms of u. And let's go about doing this. So what's our first ingredient? It's describing the region of integration in terms of the new variable u, okay? So this interval, 0 to 1, is the original interval that we're dealing with. It's you could visualize it here, just along the x-axis from 0 to 1. We're going to apply the inverse transformation on this original interval, okay? And when we do so, it's sufficient to just look at the endpoints generally. So let's look at how the inverse transformation behaves at the endpoints. So we plug in the endpoint 0 into our inverse transformation, and we get 1. And we plug in 1 into our inverse transformation, and we get 3. And so what did the inverse transformation do to this interval along the x-axis? It transformed it to this interval in the u-axis. And we could describe that new interval in the u-axis thusly. So we have the set I is equal to u, such that u is between 1 and 3. And here I just make a remark that it's oftentimes sufficient to just look at the endpoints to see how the transformation, what the inverse transformation does to the interval. Okay, so we have then our new region of integration, if you will. Originally it was 0, 1, and now it is 1 to 3. That's our new region in terms of u. So that was the first ingredient. Now what about the second ingredient? For the second ingredient, we're going to convert the integrand or function to the new coordinate u. How do we do that? Well, originally we have the function given here. Okay, this is going to be our integrand. And what we do to convert the function is wherever we see an x, we plug in the expression for x of u, which is right here, okay? Wherever we see an x, we're going to plug in this expression for x, and I just denote that expression as x of u. And so doing so, here was our x, we're going to plug this in there. Lo and behold, we get 2 square root of u, okay? So this is then the second ingredient. We've converted our function into our new coordinate system. And the third ingredient is to use this length element, if you will, to get between dx and du, to get an expression between dx and du. And using then this formula for getting the relation between the length elements, the derivative of the expression x of u with respect to u, so taking the derivative of this with respect to u, we get 1/2. Okay, so we have 1/2 du, so dx is equal to 1/2 du. And now we're going to use the formula that you see here to compute our integral in our new coordinate u. So this formula is telling you that if you have an integral over the interval ab and you want to convert to an integral using the new coordinate u, well, apply the inverse transformation to the original interval, which is what we've done above over here. Convert your function into the new variable u, which we've done over here, and use the length element that we've computed over here into this for this expression here. So we've done that there. Okay, so let's use that formula, and we have originally our integral was from 0 to 1, and this is what this means, that this is just the integral from 0 to 1. In blue, we use ingredient 1, we got the bounds of our integration, okay, by applying the inverse transformation, so we now have from 1 to 3. In green here was the conversion of the integrander function, and so we got 2 square root of u. And this last part is the length element, coming from the length element, and that's in red there, ingredient 3. Okay, so these are color-coded for ingredients, and simplifying, we have this expression here, and we may integrate and simplify to this final answer. Now, you haven't really thought about this in terms of change of coordinates. Usually it was just called u substitution. You plug and, you know, get du in terms of dx in various ways. But we've just shown that we can formally do this as a change of coordinates. So u substitution in its essence is a change in coordinates. And here I use change of coordinates or change of variables interchangeably. So you could use either expression, change of coordinates, or change of variables. We'll use both of them here. Okay, so let's now talk about change of variables for regions in R2, regions in the plane. Instead of just intervals, one variable, let's talk about 2. So if we have to do a double integral over some region in the xy plane R, we may choose to change our variables and apply a transformation, okay, and do a double integral instead over S, okay. So T inverse, the inverse transformation will go from R to S, while the transformation goes from S to T. Our transformation here, we have now x and y in terms of the new variables u and v. Moving up here, you could see the analogy that we are transforming from our old variable x, applying t inverse, to our new variable u. And how do you do u substitution in for double integrals? Well, you can't just do it with one u, right? You have two variables, x and y. So if you want, you could call this uv substitution, although I don't think anyone ever calls it uv substitution. We're instead going to call this a transformation, and the transformation moves from the maps the region S to R, in the inverse transformation the other way around. And notice now this S is in the UV plane. We're also going to need a definition here. We discussed transformations. Now let's discuss the Jacobian. Okay, and what the Jacobian is, sometimes it's written in terms of this notation. It's the determinant of this matrix that you have inside here. Okay, so if we have x in terms of u and v, if we have an expression for x in terms of u and v, then this here would be the partial derivative of that expression with respect to u. This here would be the partial derivative of that expression in terms of v. Likewise, if we have y in terms of u and v, so we have some expression huv, well, this would, for example, be the partial derivative of that expression with respect to v, and we could write all of this out. We could write out the determinant, and we have that expression here. This is called the Jacobian. It's called the Jacobian of the transformation of two variables. Okay, and what's the analogy for the Jacobian in one dimensions? Well, we computed it above this. Okay, so that right there is the analogy for the Jacobian, but for intervals rather than regions in the plane. Okay. So this theorem here will help us change variables from integrating using x and y to some general coordinates u and v, which are defined by our transformation. So let t be this transformation. So we have x in terms of u and v and y in terms of u and v. That maps a closed bounded region S in the uv plane. Okay, so here's S in the uv plane onto a region R in the xy plane. Okay, assume that t is 1 to 1 on the interior of S, in that g and h have continuous first partial derivatives there. If f is continuous on R, then we have our formula. Okay, so this here would be the double integral. This dA is in terms of x and y, so we could write dx dy, but that would be restrictive since, you know, we could change order and integrate y first, so we could have dy dx or dx dy. So that's what that dA means, and that's what that subscript means. And so if we want to do this integral instead over S in the uv plane, okay, so S is equal to t inverse of R. What do we have to do? Well, first we have to get our new region S by the inverse transformation. That will give us our bounds. Here, wherever we see an x in our original function, okay, we're going to plug in the expression of x in terms of u and v. Okay, so you could imagine this as just some expression of u and v. We would plug that in wherever we see an x, and we would plug the expression hu and v, which would correspond to y, wherever we see a y. And we then have our area element given by the absolute value of the Jacobian. Okay, and now this is a function of u and v, so it's a function of two variables. And now this dA is in terms of u and v, so we could write it as du dv or dv du depending on the order of integration we seek. So that's our formula. And let's go ahead and take a look at an example and apply it. Okay, so here we want to compute this double integral over r, where r is this square that you see here, okay? And something to notice, this integrand is not so pretty, okay? So this isn't going to be an easy double integral. Moreover, the region would have to be decomposed into two if we are going to bound this region with functions of x, or even if we choose to bound the region in terms of functions of y, we would still have to decompose it into two regions. So if we try to do this in the variables x and y, we're going to have a difficult time. What if we could find some new coordinates and make this integral much easier? Okay, so that's going to be ingredient 0, finding the transformation, finding the relation between x and some new coordinates and y and some new coordinates. So this step or ingredient definitely takes some ingenuity and creativity, but you're not completely in the dark, okay? So there's two things that motivate the choice of a new coordinate. One is the region, okay? Take a look at this region. Basically, it's bounded by expressions that look like x plus y equal to some constant. For example, here, or down here rather, this would correspond to x plus y equal to 0, for example, and x minus y equal to some other constant d. So this line here would correspond to d equals 0 there, okay? So all of these lines can be described using x plus y equal to some constant and x minus y equal to some constant. The fact that these two variables, x and y, when subtracted, give you a constant, and x plus y give you a constant, suggest that maybe we could define a new variable equal to, say, x plus y and set it equal to a constant when we do our integration. So that's one of the motivations. Taking a look at the region, we see ways to express our original variables as equal to constants, okay? And the second motivation is the integrand itself, okay? So looking at this over here, we see that the numerator has a x minus y, and we see that the denominator has a x plus y. Well, that'd be really nice, because if we had new coordinates that were equal to x minus y or x plus y, then we could separate out the numerator and denominator. Okay, right now we can't. So the numerator has both x and y, and the denominator has both x and y. But if we could define some new coordinates, then we can perhaps separate out the numerator and denominator and make the integration much easier. So looking at these two, they suggest that we should define our new coordinate u in terms of x and y as x minus y, and our second coordinate v as x plus y. Okay? Now, this is u in terms of x and y, and v in terms of x and y. That's the inverse transformation. So the transformation then is x in terms of u and v. We could just solve. So you could add these two terms together, and the y's would cancel, for example, and you could solve for x, and we get this expression. You could also subtract these two together, and you could solve for y and get the expression there. So we found our transformation, and we found our transformation motivated by looking at both the region, which was bounded by curves that respect this relation here, and by looking at our integrand. So we have our transformation, and that was ingredient 0. What is ingredient 1? Ingredient 1, as is typically the case in previous examples of coordinates we've used, is describing the region S, our new coordinate system UV, in terms of coordinates UV. Okay, so we want to describe this new region that we'll be integrating over. Now, how do we get our region S? If we have already our region R, we apply the inverse transformation. Okay, and it's often sufficient to apply the inverse transformation just around the boundary. Okay, and in fact, pretty much just the corners typically will give you a good idea of what your new region of integration S should look like. So that's what we're going to do. We're going to apply the inverse transformation on our corners in the xy plane. Okay, so for example, 0, 0. Let's apply the inverse transformation on 0, 0. Well, u of 0, 0, and again, where's the inverse transformation? It's right here. So we have u equal to x minus y. So we're plugging 0, 0 into that. We get 0 minus 0. So u will equal 0. Okay. And v, 0, 0, is 0 plus 0. And so v, 0, 0 is also 0. Okay. So where does the inverse transformation map 0, 0 in the xy plane? It maps it to 0, 0 in the UV plane. Okay. Now let's do the same thing with this other corner, 1, 1. Okay. U of 1, 1, 1 minus 1, again, just x minus y, 1 minus 1. And we get 0, doing the same thing, but with v, and v is the inverse transformation. With v is x plus y, so we get 1 plus 1, 2. So where does the inverse transformation map the point 1, 1 in the xy plane? It maps it to 0, 2 in the UV plane. Okay, so in other words, this point here gets mapped to this point there. Okay, we could do the same thing with 2, 0, and we end up getting 2, 2. Okay, so this point here, 2, 0 in the xy plane, gets mapped to this point here in the UV plane. And let's emphasize here that this is the UV plane over there. And likewise, minus 1, likewise 1 minus 1 gets mapped to 2, 0. Okay, so this point here gets mapped to 2, 0. So it's essentially this transformation rotated and stretched out the original square that we had there in the xy plane. Okay, so then this, doing it just on the corners is sufficient oftentimes, and this then is our new region of integration. Let's describe it. It's described in this manner. So S in the UV plane, U is going to be between 0 and 2, and V will be also between 0 and 2. That's our first ingredient. Okay. Now our second ingredient is typically what? Yep. Convert the integrander function to the new coordinates. Okay. So here we have our original integrand. Okay. In terms of a function of two variables. And what do? We plug in the expressions of x in terms of u and v. So wherever we see an x, we plug in 1/2 u plus v. Where did we get that? From not the inverse, but the actual transformation, okay? The forward transformation, if you will. So not the inverse. So here's x in terms of u and v. And so wherever we see a x in our form, in our function, we're going to plug in 1/2 u plus v. Wherever we see a y, we will plug in 1/2 v minus u. Okay, so that's what we would get if we plugged in these expressions for x and y, and when we simplify, we get the square root of u over v plus 1. Now, of course, one may say, well, it's easy to notice that that's just equal to u right there. And that's absolutely fine. I'm just giving a systematic way for you to do this, even if the function was a little more complicated. Okay? And our final ingredient is to compute the area element, okay, in terms of our new coordinates u and v. So here is subscript uv. We want the area element in terms of u and v. And to use the other ingredients in the formula above in the theorem. So to get our area element, we need the Jacobian. Let's compute it. So we have here the partial derivative of x in terms of u and v with respect to u, okay? And so we go up here, let's look at x in terms of u and v and take the partial derivative with respect to u of this. Well, that's just a half. Taking the partial derivative of x with respect to v also is a half. Taking the partial derivative of y with respect to u gives us minus 1/2. And taking the partial derivative of y with respect to v will give us plus 1/2. Okay, so that's what you're seeing here. Okay, so this was partial y partial u, for example. Take the partial derivative of this with respect to u and you get minus 1/2, and the rest are halves. Let's take the determinant of that. So 1/2 times 1/2 minus 1/2 times negative 1/2, and that should be equal to 1/2. And so our area element then is equal to the absolute value of 1/2 times du dv. And so we have our new area element here in the UV plane. So those are the three ingredients. Okay, of course we needed ingredient 0, but once we have these three ingredients, we plug them in our formula. We have our bounds of integration coming from ingredient 1, the description of the region in terms of the new coordinate system. So that's our bounds for the that's coming from ingredient 1 in blue. And in green here is the conversion of the function, okay, in terms of the new variables, and that's what we have here. And in red here is the area element, okay, and we computed that thanks to the help of the Jacobian, and we then simplify and integrate. So we'll integrate and then simplify, and then we're left with a straightforward double integral to do that. Had we not changed coordinates to these very useful u and v coordinates, would be quite difficult. Here we've done it in just a couple of steps, and this here is our final answer.